Hello everyone, and welcome to the real-world applications of calculus. We first begin with the basics. A derivative is the slope of any curve at a certain point. The dy and dx length are infinitesimally small. On the other hand, integration of any function is the area under the curve within a certain bound. This leads right into the first application of calculus, which is in geometry. Say we have a circle of equation x squared plus y squared equals to 4. First, we manipulate this equation and isolate y to get it as a function of x. We can find the area in parts. The first part can be calculated by integrating this equation from 0 to 2. We apply trig substitution by letting x equals 2 sin theta, then dx equals 2 cos theta d theta. After simplification, we use cos 2 theta formula. Finally, we get pi. This means the whole area is 4 pi. Next, the field for which calculus was invented in the first place, physics. Let's derive one of the equations of motion. The acceleration of a body is the derivative of velocity with respect to time. After rearranging, we can integrate on both sides. As the body accelerates from initial velocity u to final velocity v, the time goes from 0 to t. This gives us one of the fundamental equations in Newtonian physics. Next up, economics. The Lorentz curve is a graphical representation of the distribution of income or wealth in a society. Basically, the farther the curve moves from the baseline, represented by a straight diagonal line, the higher the level of inequality. If X population receives f of x of income, assuming the total income of an economy as 1, the remaining income 1 minus f of x is distributed among the remaining fraction of population 1 minus x. This remaining fraction is the richer section, and the average income of all richer individuals will be represented by 1 minus f of x by 1 minus x. The individual with income x is supposed to have a constant fraction, delta, where delta is less than 1. Further, if an individual's contribution to Lorentz curve is the derivative of the curve, then this equation is a linear non-homogeneous differential equation. Lastly, let's see how calculus is used to approximate solutions to functions. Imagine a function f of x whose solution we want. We start with an initial guess x1, we then calculate f of x1. If f of x1 is 0, we have a solution, but most likely f of x1 is not 0. We then draw the tangent line at the point where our initial guess intersects with the function. This tangent line is a good linear approximation to f of x near x1. So our next guess x2 is the point where this line intersects with the x-axis. We proceed with the same method as the approximation gets closer to the true value. This method for finding a solution is Newton's method. Let f of x from R to R be a differentiable function. We seek a solution of f of x equals 0 starting from an initial estimate x equals x1. At the nth step, given xn, compute the next approximation xn plus 1 by xn plus 1 equals xn minus f of xn by f prime of xn. There are many more applications of calculus in the real world. This much for today. Thank you for watching.